Hello everyone, this is Hu Shaochi from Peking University. Today, my topic is a contrastive learning-based method for alerting categorization. Over the last decades, drastic progress has been witnessed on advanced driver assistance system, that is ADAS. One important ADAS function is that it should alert human driver to take over control when there is a dangerous situation. But the question is, when to alert a driver? In this paper, we formulate the problem as alerting categorization and solve it by learning from driver's weak supervision. The problem formulation is below, giving a front view video of a driving scene, which is marked with anchor points. The semantic attribute of neighbor anchor is different, and there is an assumption. Video is temporally continuous, that is, the neighbor frame of an anchor has the same attribute of the anchor. And our purpose is learning a category profile to model the driving sense of different semantic category. Then we can infer scene labels for input image. Our algorithm pipeline is shown in its page. First, a feature encoder is learned, and then driving scene is profiled. Finally, we can do scene categorization. Now we introduce the feature encoder learning. So for a feature encoder f theta, it converts image I to feature space ZD. And it is trained by contrastive learning method. And the scene similarity of pair images is defined as the cosine similarity of two feature vectors. So for contrastive learning, the sampling strategy is giving a query pointer Q. Its one positive sample Q plus is randomly selected near the anchor Ki, and its negative sample Q negative is randomly selected from neighbor anchor of Ki. And the loss function is defined as input NCE loss. For the driving scene profiling, we first describe how to generate scene descriptor. So given a query image Q, we first calculate its similarity with each frame in training video, and we can get a set. Then we can get a histogram on the above set to obtain its scene descriptor DSQ. Now we can generate the category profile. Given scene descriptors of each frame in video, we can get a set D. We select a typical image QC for each category C and compare its scene descriptor DSQC with other DSP in D. Then we can get a subset by JS diversity. The category profile CPC is an average scene descriptor on DC. For the scene categorization, given a single image Q, we first estimate its scene descriptor DSQ, and then compare DSQ with each category profile CPC by JS diversity. Then we can predict the label by minimizing the diversity, as shown in this figure. Now we go to the experiment component. So first, the experimental data is the video data is collected in the campus of Peking University, and we totally got 40 minutes with so many frames at a frame rate of 15 FPS, and we totally got 242 anchor points. The baseline method are two end-to-end classification models, and they are trained in full supervised way. They are only different on the training dataset. For baseline 1, it is trained only on the 242 anchor points, but for baseline 2, it is trained on the anchor points with their neighbors. This page shows the feature encoder and sense similarity learning. Figure A and B shows the feature visualization on anchor points and all frames. These two figures shows it's hard to split different classes only by feature and proves the necessity of category profiling. Figure C shows the average similarity between different categories, and the figure D shows the similarity between query frame and other frames, which are shown on trajectory. Red for similar and blue for dissimilar. The above result proves our method learns a semantically matrix to evaluate the similarity between things. This page shows the feature encoder and sense similarity learning on the trajectory level. First, we choose a trajectory and a query frame. And the above is the semantic similarity between current frame and the query image. With the video runs, we can see the current frame and the query image similarity. And the similarity shows the result of our learning. This page shows the same categorization result. Both quantitatively and qualitatively result shows our algorithm is good to discover alert thing. This page demonstrates the classification process. It is categorized as red rectangle. An alert thing is detected. Another alert thing is detected. Here comes to the conclusions. This paper proposed a learning-based model to categorize things that ADAS should alert a driver, and the contrastive learning method is used to train the feature encoder on humans' weak supervision. Category profile is modeled to capture the meta pattern of each class, and the proposed method surpassed the conventional end-to-end full supervised method. And the future work is how to generate the ground truth data and how to evaluate performance in ambiguous situations. Thank you.